before we get started, please make sure that you have printed the full PowerPoint so that you have the PowerPoint notes to take your notes as we proceed. On your notes, you'll notice that the polynomial is written much better than the way it shows up on this slide. So we have a polynomial x to the third, 4x squared minus 5x minus 14. If we want to find the zeros of this, we could use the p over q, finding the factors of 14 and the factors of 1 in front of the x to the third. And we will use our graphing calculator to help us narrow the search of what those factors might be. So if x equals 2, that 2 value there might be a good option to pick to use either synthetic division or long division in this case to find the reduced or suppressed polynomial q of x. Our goal here is to get any higher order polynomial, a cubic, a fourth degree, a fifth degree, down to a quadratic right here and right here, down to a quadratic where we could either factor or use the quadratic formula to find the rest of the roots of our quadratic equation. Just to get our terms straight here, if we're talking about using polynomials and we're dividing through with our polynomials, we would start with the original polynomial p of x, and when we perform our division, the polynomial we obtain, d of x, is the divisor. Q of x would be what comes out, the quotient, and if it's not a factor, we would have a remainder, r of x. So let's give our long division a try. On your paper, it's easier to see what our original polynomial is. It would be x to the third plus 4x squared minus 5x minus 14. And we want to try using long division with x minus 2. So let's see what we can do with x minus 2. Goes into x to the third plus 4x squared minus 5x minus 14. Okay, so x times what gives us x to the third? That would be x squared. And then I take my x squared and I multiply everything out in front of the division symbol. So that would take x cubed, and I'd have a negative 2x squared. But if you think about division, we have to subtract all of that. So that's going to change my signs entirely. So that'll cancel my x to the thirds, and I would wind up with 6x squared. And now I'm thinking x squared times what gives me x? Well, that sounds like plus 6x. So I'm taking 6x times everything out in front, and I would have 6x squared minus 12x. And now I need to subtract all that, so I change the signs. And let's see what happens. The 6x squareds cancel. I now have negative 5x and positive 12x, so that sounds like 7x. So x times what gives me 7x? Well, that would be positive 7. So 7x, and then minus 14. And what do you know? We have a remainder of 0. So it's kind of hard to see what I wrote up there on top of all the letters, and if I can read my handwriting again, we have in our nice notation from before with the D's and P's and Q's and R's and whatever else they had. It was x squared, or x minus 2 times the x squared plus 6x plus 7. And I have no remainder, so I don't have to worry about it. And this would be my final answer. Now, if I wanted to divide the second one, the first thing I'm going to do is erase everything that's in here. Maybe. Hold that thought. Okay, so if we have the x squared minus 1, and then I'm dividing into x to the third plus 9x sometime this will write. So I think x squared times what gives me x to the third? That would be an x. And then I multiply everything in front of the division symbol. I would have an x to the third and an x, a negative x. And then I have to subtract everything that was in there. Then that would let me cancel the x to the thirds, and I would have 10x. And as I look at x squared, and I think x squared times what gives me 10x, nothing's going to help me there. So I'm starting to get a remainder. I would bring down the minus 5 for my polynomial. That is my remainder. So when I write this as what times what, I would have x squared minus 1 times x, and then 10x minus 5 over x to the third plus 9x plus 5. Okay, so the remainder theorem helps us out when we're using synthetic division, which we're going to get to in a minute. The remainder theorem also helps us quickly tell if we have a factor or not by using our function notation. If we get a value of 0 when we plug in whatever value we want to check, then we know that we have a factor. If we plug in a value and it's not 0, it's not a 0. We have a remainder. So let's check this out quickly using the remainder theorem. Let's say we have a polynomial 5x to the third minus 2x squared plus 1, and I want to check to see if x minus 3 is a factor. Well, I can quickly do this if we take f of the 0 for this would be at x minus 3 equals 0 or at x equals 3. So I'm going to use the value f of 3, and I'm going to plug it in to my original polynomial, 5 times 3 cubed minus 2 times 3 squared plus 1. And if we do a little quick calculation, we find out that this gives us 118, which is clearly not 0. So at positive 3 on the x-intercept, we have an ordered pair from our function notation, what we know. We have an ordered pair of 3, 118, which is clearly not crossing the x-axis anywhere. So this value is not a 0. Not a 0. X minus 3 is not a factor. Not. So this is a very quick way to check to see if we have factors before we get into synthetic division. Synthetic division is where we're headed. Okay, so let's try using synthetic division on x to the third plus 8 divided by x plus 2. So synthetic division, again with our finding the 0, we would take x plus 2, if I can write. Okay, so the x plus 2 equal to 0 occurs at -2. So that -2 value is what I'm interested in out in front. That is going to divide into all the coefficients that are in our original polynomial. So there's a 1 where we had x to the third, we have no x squareds, no x's, and 8 constants. And then I'll bring down the 1 and I'm going to multiply by -2. I add the 0 and -2, and I multiply the -2 and the -2 that I have as a result of addition, which would give me positive 4. Add the 0 and the 4 to get positive 4, and then multiply -2 times positive 4 to get -8, and lo and behold, we get 0. So x plus 2 is a factor of the original polynomial, and what we have down here, again, that's called the suppressed polynomial. It decreases in degree. So this was an x to the third from what we had over here. We would have x squared minus 2x plus 4. And now that we've gotten it down to a quadratic, we could find other roots either by factoring or by using the quadratic formula. Our goal is to get to a quadratic, so this is good news. If we look at this fourth degree equation, we have two factors that we need to show are factors by using synthetic division. With the x minus 2, we would have a root or a 0 at positive 2. And then with x plus 3, we would have a root at -3. And so we're going to use those two values in our synthetic division. It doesn't matter which of those values we begin with first. I'm going to start with the 2 simply because it becomes first in the problem. And our goal is to use those two values to take our fourth degree polynomial down to a second degree polynomial, so we can then use either the quadratic formula or factoring or whatever other methods we know how to solve a quadratic equation and find the other factors or roots or zeros of g of x. So let's see what we can do with 2 in our synthetic division. So there's 2. Okay, so we bring down the 2 and we multiply by the 2 out in front. And lo and behold, we get a 0 as our remainder. That is our proof that we have x minus 2 with the value of 2 as a 0, as opposed to just using your graphing calculator and seeing that it looks like it crosses the x-axis at 2. Now we have to reproduce this work with the negative 3, and so I will use the suppressed equation, or the suppressed polynomial, using the negative 3. So I bring down the 2, and thankfully that also gave us a 0. So again, that's the rest of our work to tell us that we have a 0 at negative 3. The fact that we have zeros tells us the original factors that we wanted to demonstrate, the x plus 3 and the x minus 2, are indeed factors, but we now have a quadratic 2x squared plus 5x plus 3 that we need to set equal to 0. So you might be really good at factoring, but I'm terrible at it, so I'm going to use the quadratic formula. So this is telling me that x equals plus or minus negative 4 over 4. Sorry, not plus or minus. That x equals negative 4 over 4 or negative 6 over 4. So I would have x equals 1 or negative 3 over 2. So if I wanted to find all of my factors, with x equals 1, I would have a factor of x minus 1. And then with x equals negative 3 halves, I'm going to multiply by 2 on both sides. So now I have 2x equals negative 3. I'm going to add 3 to both sides. So I have 2x plus 3 as my other factors, and I now have 4 factors and a 4th degree polynomial, which seems pretty reasonable. In terms of multiplicity, we looked at multiplicity in the last section as to how it would impact the graph. If a 0 has multiplicity of 1 or 3, it will cross the graph, but multiplicity of 2 or 4, it will touch the graph and then go back up or back down. So it briefly touches the x-axis. If we're talking about it in terms of finding roots or zeros, in synthetic division, that means we can use the value more than once. So in this example, where we have a 0 of multiplicity 2, we can use that 1/2 twice in our synthetic division. And so let's start with 1/2, and then all the values from our polynomial. To get our suppressed equation. And as we work through the first usage of the 1/2, we get a remainder of 0, indicating that it is a 0, or x minus 1/2 is a factor. And if it says x minus 1/2, we would really write that as 2x minus 1 would be our factor. I can now take the suppressed equation and use the 1/2 again to see what else we can find. And lo and behold, we get another remainder of 0. And in the process, we went from a 4th degree down to a 3rd degree, and now we're at a quadratic. And we know how to solve quadratics quite easily. I have 4x to the 4th minus 12, and I need to set that equal to 0 to solve for x. So the first thing I could do is factor out a 4. And actually, I think that's minus 3, not minus 4. And then, if I wanted to, I could say x squared equals 3, take the square root of both sides, and whenever you take the square root, you need a plus or minus in front, so x equals plus or minus the square root of 3. So I now have 4 roots, or zeros. I have plus or minus the square root of 3, and I have 1/2. It just happens to be 1/2 twice. If we're talking about the number of zeros that we can possibly have, we can have at most n. That would match the degree, the highest degree of our polynomial. But this would include the multiplicity of whatever 0, and that would be the number of real zeros. So this doesn't count any imaginary zeros. Okay, so let's talk about how zeros and roots and solutions all are connected. First things first, if we talk about zeros, roots, and solutions, it's 3 words that mean exactly the same thing. So if we were to say that we had a solution, let's say x equals 2, that tells us a couple pieces of information. If x equals 2 in our polynomial, that's a solution, then that means that at 2, the graph crosses the x-axis, so the y value is 0. If the y value is 0 at 2, then that also tells us in our polynomial, if polynomial p, if we plugged in 2 into the entire polynomial, we would get a remainder of 0. It also tells us that if we were to take x equals 2 and add 2 to both sides, subtract 2 to both sides, we would then get x minus 2 equals 0. Here's where those zeros are coming from. And this x minus 2 would be a factor of the original polynomial. And so hopefully this helps you see the relationship between our zeros, our x-intercepts, the remainder theorem, the solutions, all the things that we've been discussing today. And where we're headed tomorrow is how do we find these factors without them being given to us. From the example we did before, we found that this polynomial had zeros at plus or minus the square root of 3 and zeros at one-half multiplicity 2. So if we take a look at what that does on our graph paper, plus or minus the square root of 3 is approximately, it's not exactly, but it's in between positive 1, or negative 1 and negative 2, and in between positive 2 and negative 2, and having it at 1/2 is about in there. We also know that this is a positive fourth degree equation, so based on our knowledge of fourth degree equations, it being positive and even, the graph should do something like this in terms of end behavior. We don't know quite what it's doing in the middle. Well, now we do. We have a better idea of the zeros, but it should be pointing up in both directions on the left and on the right. So let's see what happens. It would come down, cross, then touch here, go back down, and then cross, and go back up, off towards positive infinity in both directions. I don't know exactly how far down it comes in the negative values around the y-axis. I just have a general guesstimate for that, but I do know where it crosses on the x-axis, and I do know what the end behavior is doing. I also have this value. That's my y-intercept. I didn't do a very good job of plotting that, but you'll do a better job. I should have included negative 3 on my graph. And then we have a pretty good approximation of what this graph would be doing.